So to compute the flux of a vector field through a surface, if I have a parameterization for that surface in hand, then we want to first of all use that parameterization to come up with our normal vector field in the ways that we've been talking about so far today. Right? Take the cross product of the derivatives of our parameterization. That's going to give us a normal vector field. It's also going to define for us which direction is positive, right? Because that normal vector is either going to point towards one direction of the surface or the other direction away from the surface, depending on which order we take the cross product. So we should always try to keep our head on a swivel here, so that we know which direction is being counted as positive. We should always kind of check after you take that cross product to make sure that you know which direction is being counted as positive. But then what it ultimately comes down to is that to find the flux, we're doing exactly the same kind of thing that we were doing in 2 dimensions. We're taking the dot product of our vector field with this normal vector that points out of our surface. If we were parameterizing our surface or sort of describing our surface in any other way besides coming up with a parameterization and taking the cross product of the derivatives, then we would have to worry about having a unit normal vector to our parameterization. But when we do it this way, we actually don't have to worry about that, because different parameterizations are going to give us parameterize the surface in different ways, and that difference actually washes itself out in this case. So we don't have to worry about making this a unit length normal vector. We can just take the dot product of f with the cross product of the derivatives of our parameterization, which is our normal vector field, and take the double integral of that in parameter space, so in ST space. So your integral here is going to end up being an integral ds dt or dt ds, depending on which order you find is easier to tape measure your region in parameter space over which s and t range, and then to actually do the iterated integral that succeeds in this case. So our next activity is to do one of those calculations, and that begins with picking a vector field, y, z, 2 plus sine x. So there's our vector field. And our surface is a right circular cylinder of radius 2 and height 3, and its top and its bottom are open. So this is not the whole can of soda, it's just the label on the side of the can of soda. I guess soda cans don't have labels, but you know what I mean. So it's just that part of the cylinder that goes around. And here is a visualization of our vector field. And I don't know. So the first task might be to look at this diagram, and there's a link again in the activity stream for you to click directly here, or you can just scroll down from where you were at a moment ago, and just see if you can figure out whether or not this should be a positive or a negative flux before we actually do the integral. And in order to make that decision, we need to know which direction our normal vector is going to point. And so here we're sort of given that to us before we do any calculation, that if we consider the flux going into the cylinder as positive, so a normal vector that points in towards the z-axis as positive flux, then that'll be the direction that you use to try and reason graphically about whether this total flux is positive, negative, or 0. And then once you've made that prediction, you'll parameterize this cylinder, and then compute that normal vector field, and then evaluate this flux integral. So it's the vector field evaluated on the parameterization r of s and t, dotted with the cross product of the derivatives of our parameterization, and then integrated in parameter space ds dt to compute the flux of this. So there is a part B and a part C and a part 7, and I don't think we have time to go through all those, so your task is going to be parts 1 through 6 of part A, which just deals with this vector field and this surface. First, make the prediction of whether the flux is positive, negative, or 0 if the surface is oriented with the normal vector pointing inward toward the x-axis, and then do the parameterization and do the direct computation of the flux integral to verify your prediction. I speak in long sentences sometimes, so I apologize. That was probably much longer than a sentence should have been. But anyway, let's take a generous 15 minutes, maybe longer, to do the work on the direct evaluation of this flux integral. You parameterized this cylindrical patch of surface using a cylindrical coordinate help here, 2 cosine s, 2 sine s, comma t, s ranging from 0 to 2 pi, t ranging from 0 to 3. Computed the derivatives of that parameterization, and then the cross product thereof. Got 2 cosine s, comma 2 sine s, comma 0. And that 0 is super helpful because when you go to take the dot product of f of r of t with the cross product of rs with rt, your integrand ends up being 4 sine s cosine s plus 2t times sine of s. And that's all. You have to integrate that, ds dt. S ranging from 0 to 2 pi, t ranging from 0 to 3. And what happens is that all of the s dependence on here ends up wiping out on the interval 0 to 2 pi to a value of 0. So the net flux into / out of this surface and this vector field right here, there is evidently exactly as much vector field going into the soup can label here as there is coming out of the soup can label. And so the net flux ends up being 0.